We're going to get into related rates here. And I think the easiest way is for me to just start doing some problems. So I just printed off. There's your homework and your work for tomorrow. So just do probably, 3-4 problems tonight. Make sure you have some idea what's going on, then bring it in tomorrow and we'll do the rest. So number 1 is an example that you're going to wait till tomorrow. So we will go through that one. That's tougher. It's got some extra stuff in it. So we're going to wait on that. I'm going to jump to number 2. So, what this means is we got a balloon. You got a sphere. So, something going on like this. And the radius is increasing. Well, the thing is, if the radius increases, so does everything else. If the radius is getting bigger, then the volume is getting bigger. The surface area is getting bigger. The diameter is getting bigger. Like, all of this stuff goes with it. And it's all changing as time passes. So time has to be involved in a related rates problem. And if you see here, it's got this centimeters per second. That's one clue that you're doing related rates. Another one is just you got multiple things changing as time passes. So just kind of reading through the context. But what's happening is this balloon's getting bigger. So we're going to start labeling things that we know. And there's 2 different ways you label things. So right here, they tell me that the radius is 9. That's r equals 9. That's no problem. That's just like very typical. Right here, they tell me the radius increases at a rate of. Well, increase at a rate of, rate means derivative. So if we take the derivative of r with respect to time is what we're doing here, it ends up being dr dt. So dr dt is 3 over r. So there's a difference between these. This is the radius is 9. So this balloon is getting bigger and bigger and bigger. And at that instant when it hits 9, this is how fast it's changing. This is like your original. This is your derivative. This is an amount. This is a rate. This is like position. This is like velocity. And then I can go a step further here and say, okay, well, that's just 3 over 9. So dr over dt is 1/3. They're asking for how fast is the volume increasing. Again, that's a rate. So they're not actually asking for v. They're asking for dv over dt. So dv over dt equals what? I could find the volume. I'm never going to need it, and you'll see why. But v would be separate from dv dt. So I need to know the equation that relates all of this information. So what's the equation for the volume of a sphere? This volume equals 4/3 pi r cubed. I've never seen that not given to you, so you don't really have to memorize them. They'll just kind of be there. Now you're going to take the derivative of that, because this is an amount. This is a position. I want to get to the rate level, where I can start working with the rate of change of the radius and the rate of change of the volume. So I'm going to take the derivative of this. It is just like implicit differentiation. So whenever you took in implicit differentiation, whenever you took the derivative of a y, you multiplied by dy over dx. Here, when I take the derivative of any variable, it's changing as time passes. So I'm going to multiply by d, whatever that variable is, over dt. So the derivative of v is 1. But I took the derivative of a v, so I multiply by dv dt. Simplest way to think about that is that's your position, that's your velocity. So here's your volume, here's the change in your volume. Now take the derivative over here, bring down the 3 times 4/3. 3's cancel, you get 4 pi r squared, but you took the derivative of an r, so you multiply by dr dt. And now, well, this one is like your original. This is your derivative, which talks about rates of change, and that's when we can start plugging in all of our stuff. So dv over t is going to equal 4 pi times 9 squared times 1/3, which would be, I believe, 108. I'm not really worried about the answer. You guys can put the answer. And it would be centimeters. It's volume, so it's centimeters cubed per second. And they do ask you, so they don't always grade the labels, but sometimes they'll say, make sure you label it. And if they say, make sure they label it, they're going to grade that. So you want to make sure you know how to do the label. That's bothering me that I don't have an answer. Hold on. 9 squared times 4. So 108. Alright, let's look at 3. So this is another one that's not too bad. It's not like number 1 where you need extra information or something weird. So we got a perfect cube, shaped ice cube. So I know it's a cube, so this is like x, x, x. The black would change its cube shape as it melts. And it's melting at a rate of this rate, so that means that we're looking at volume, because this much of the ice is going away, and I can tell it's volume because it's cubed, so area would be squared. So I know the volume of a cube is length times width times height. The volume of this cube is x cubed. So what this tells me here is that dv dt equals negative 64. Sides are 5, so that tells me x equals 5. What rate are the sides changing would be dx over dt, and that's what we want to know. So we're going to take the derivative and plug in. So the derivative of v is 1, but I took the derivative of a v, so multiply by dv over dt. Derivative of x to the third is 3x squared, but I took the derivative of an x, so multiply by dx over dt. And then this is negative 64. X is 5. So if you work that out, dx dt would be negative 64 over 75 centimeters per second. That's just a length. So length is just centimeters. Area would be centimeters squared. Volume would be centimeters cubed. Alright. Let's do, so this is another one I'd like you to skip and wait till tomorrow. 5, we did one similar. 6, we did one similar. Looks like it's 7. 8's a Cohen one, which those are the tougher ones. So we'll do 7. Crowd gathers around a movie star forming a circle. So you got your movie star, and then you got like more and more people are coming. So the circle's getting bigger, which means the radius of the circle is getting bigger, the diameter, the area, the circumference, all that stuff. They're asking about area. So right away I see area and I see circle, and I'm going, okay, area equals pi r squared. The area increases at that rate. So that is not A, that is dA dt, because it tells you how fast the area is changing. R equals 12. How fast is the radius increasing? That's dr dt. That's like the velocity of the radius. That's what I'm looking for. Area is pi r squared, so start taking the derivative to get down to the velocity or the rate level. Derivative of A is 1, but you took the derivative of an A, so multiply by dA dt. Bring down the 2, and this derivative over here would be 2 pi r, but you took the derivative of an r, so multiply by dr dt. And then plug in. You know this is 36. You know that's 12. So dr dt comes out to be 36 over 24 pi. And this would be feet per second. And you're totally allowed to leave your answer with that pi in it. All right, so I think I'd like you to at least try 5 and 6. 5, 6, and 7. 5, 6, 8, 9. Let's say that. Try 5, 6, 8, 9. We'll check those over, talk about the cone ones, and look at anything else that might be a little tougher tomorrow.